Welcome to the Explainer. If you're a focused learner looking to squeeze literally every last drop of performance out of your software, well, you're in exactly the right place. Today, we're taking a deep dive into high-level Java performance optimization, specifically focusing on Java's 90-10 performance rule. But don't worry, we're going to leave all that dense compiler jargon at the door. Instead, we'll unpack exactly how modern Java gets so incredibly fast, step by step. Okay, let's dive into this. Have you ever stopped to wonder, what if a massive chunk of the effort your system puts into code optimization is, well, completely useless? It's kind of a shocking thought, right? We're so conditioned to believe that highly optimized code is good code, everywhere, all the time. But when you look at how applications actually execute under the hood, treating every single line of code as equally important, it's a huge misconception. And honestly, it's a massive waste of resources. And this brings us to a major turning point in how we understand application execution. It's the 90-10 performance rule. This single ratio fundamentally flips how modern compilers look at the software we write. It's not just some rough estimate either. It's a mathematically proven metric that forms the absolute bedrock of next-generation performance tuning. Now, what's really interesting about this slide is the stark visual contrast. For typical programs, 90% of the execution time is spent running just 10% of the actual code base. Just let that sink in for a second. The vast majority of your application's lifecycle is spent looping over a tiny fraction of your code. We call this 10% the hot code, and the remaining 90%, that's the cold code. Understanding this completely reframes the classic conflict in compilation strategies. On one side, you've got traditional static analysis, which we often see in ahead of time or AOT compilation. It's incredibly thorough, sure, but it's also totally blind. It allocates equal computational resources across the entire code space, basically just guessing what might be important. On the flip side, we have runtime profiling, used by just-in-time or JIT compilers. This actually watches the code execute, so it knows precisely where those dynamic hotspots are on the fly. The underlying problem is that purely static AOT compilation treats all code equally, which, as we just saw, is highly inefficient. So think about the computational budget of a compiler. If we know the 90-10 rule holds true, we really have to ask ourselves, why infer precise, deep-level information for cold code? Why blow precious memory, time, and CPU cycles hyper-analyzing a block of code that might execute exactly once, or maybe literally never, during the entire lifespan of the application? It's like buying $1 million high-performance sports car just to leave it permanently parked in your driveway. Let's move to, and see how this builds as we enter Section 1, the adaptive solution, bridging the gap. We have this optimization dilemma, right? Static analysis is blind to hotspots, but dynamic profiling happens a bit too late. Enter adaptive static analysis. This is an elegant bridge between those two worlds. It uses dynamic runtime information to automatically increase analysis precision, specifically for that frequently executed 10% of code. It intelligently trades analysis cost for performance. By feeding dynamic profiling data right back into the static analyzer, the system knows exactly where the hotspots are, so it can drop its heavy computational budget only where it actually matters. So, the crucial point is captured perfectly in this quote from the joint research by Oracle Labs and UC Irvine. To maximize application performance, an analysis should focus on increasing the precision of frequently executed code. That right there is the core philosophy. You don't optimize everything. You deeply, aggressively optimize the stuff that gets used to most. Let's break down the mechanics of this 3D design space. Standard analysis traditionally balances just two dimensions, analysis cost versus results precision. But adaptive analysis throws in a vital third dimension, execution frequency. Think of it like a home renovation. You're going to spend your entire budget on the living room and the kitchen, the spaces you actually live in every single day, rather than dropping 10 grand on a guest bedroom closet you open maybe once a year. In Java terms, the hot code gets highly accurate, object abstraction, and increased context depth. Meanwhile, the cold code gracefully falls back to basic, cheaper analysis methods to save resources. Section 2, Real-World Performance, Java in Action. That all sounds fantastic in theory, for sure, but let's look at the concrete proof. The data from the study is just staggering. Researchers compared standard static analysis against this runtime-profiled adaptive approach, and the gains in accuracy are massive. For frequently executed virtual calls, accuracy went up by a solid 10%. But look at the type checks. For frequently executed type checks, accuracy skyrocketed by 73%. When the static analyzer is guided by actual runtime profiling, it can eliminate the need for those costly de-optimization guards that bog applications down simply because it finally knows exactly what types of objects it's dealing with.
And this brilliantly illustrates that exact point across industry benchmarks like DeCapo and SpecJVM. What we are looking at are virtual calls that are never executed. The dynamic model proves that vast swaths of code predicted as necessary by static analysis are, in reality, completely untouched during runtime. It just shows you how much effort static analysis wastes on things that literally don't even happen.
So where is this actually being used today? Well, this cutting-edge adaptive static analysis is integrated directly into the Graal compiler pipeline. It leverages the robust runtime profiling of the Java Hotspot VM, and by combining the two, it makes ahead-of-time Java compilation incredibly efficient. The resulting executables have a smaller footprint, they start up way faster, and they use less memory. It's basically the absolute ideal optimization strategy for modern, fast-paced cloud and microservice architectures where literally every millisecond counts. It really makes you rethink how we approach performance entirely. As we wrap up this explainer, I want you to look at your own workflows and ask yourself, is your application dynamically adapting to its hotspots? Or is it just freezing in the cold, wasting resources on code that never even runs? Thanks for hanging out with me to explore Java's 90-10 rule. Keep learning, keep optimizing, and I'll catch you in the next explainer.